Okay, welcome back to our Chem 1331 lecture series and discussion. We're getting close to the end of the term, and so we're wrapping up. This will be the last chapter, I believe. This is the last chapter for this term. It's a long one. It's a lot of stuff going on in this, and a lot of detail. More a lot of detail than any sort of mathematical or calculational information or lots of equations to memorize. There are a couple, but a lot of concepts that we'll need to talk about, and a lot of concepts that are important to pick up and understand as we move along. So liquids and solids are, of course, around us all the time. Here's the liquid that I'm drinking right now, my cup of coffee. That's a liquid, and it's in a solid cup, as we can all say. Here's my hand sanitizer right there. It's ethyl alcohol in a little spray bottle. Use this a lot during the shutdown and so on. But I think we all have a cursory understanding of what a liquid and solid is. We talked about gases, and now we're going to talk about a liquid and solid. A solid, the main thing about a liquid, we can see in this little bottle of hand sanitizer, is that it conforms to the container that it happens to be in. And in fact, in this little hand sanitizer, there is a liquid phase. This is ethanol, and above that is a mixture, rather, of ethanol, water vapor, and ethanol vapor, water vapor, and air, and at atmospheric pressure. And from what we talked about the last time, there's a partial pressure of ethanol above this. If you open this up and smell it, you could smell the alcohol. And the water vapor that happened to be latency in the air. And we could calculate that the total pressure, going back to chapter 8, of the air or gas inside this little part up here is the sum of the partial pressure of the ethanol that's continuously evaporating and being cycling back and forth in equilibrium between the ethanol down here and the ethanol vapor here. We'll learn about what's called vapor pressure in this term, in this part. The vapor pressure is related to the boiling point. So the higher the vapor pressure, the lower the boiling point. And when the vapor pressure of the liquid is equal to the atmospheric pressure, things boil. Okay. And we'll talk about what changes the vapor pressure and the boiling point of a liquid. And I don't think we'll talk about how one can calculate the vapor pressure of the gas above a liquid. I believe that's something we do in physical chemistry, because we need to use the Clausius-Clapeyron equation to do that, which I don't believe we'll talk about in this term. We can derive it. If you want, I can give you a quick lecture on Clausius-Clapeyron. It's straightforward to get, but the main thing to understand is that in a liquid, there's an interface between the liquid and the gas. Generally, we consider the gas to be above the liquid because the gas is much lower density than the liquid, and so on. So let's continue. And I still haven't solved the focusing problems on my webcam. I think it's just something that's just a problem with these little small webcams. They're just not designed to be set up for this. So since this is a chemistry class, we need to talk about what causes a liquid to form a liquid. Here's my liquid, and what differentiates different kinds of liquids, and what causes liquids, for example, to phase segregate. So for example, if I have another glass, another thing of I don't think you can see it. Maybe you can. A little bit of oil that's in the bottom of this. Is there? Yeah, I can see a little bit of oil that's in the bottom of this. You can see little droplets of oil. This was some oil that I added to the alcohol just to make it smell nicer for hand sanitizer. But you can see, maybe you can see little droplets of oil that are down there in the bottom of this. And that is just some olive oil, and it's phase segregated from the ethanol that is above this. You can just see a little bit down there, maybe around the bottom. If I added more ethanol or olive oil, you would see more. And I just did that because when you use hand sanitizer, it dries your hands out, and the oil sort of keeps your hands a little nicer. But it demonstrates the fact that liquids will phase segregate due to differences in intermolecular forces, and we'll talk about that. So, in the first part of the course, we talked about intermolecular bonding. That is the bonding network within the molecule itself. Those are very strong, typically covalent or ionic bonds. Many electron volts of energy, many kilojoules per mole of energy, hundreds of kilojoules per mole to break a chemical bond. Consequently, if the molecules of ethanol that are inside this little bottle are in the liquid part molecules of ethanol. They are ethanol, which is, let me write out the equation of ethanol. Ethanol is CH3 CH2OH. It's ethanol. And in fact, this is 100% ethanol in a liquid, or 200 proof. Just in case you are interested. So the molecules that are inside the liquid down here are ethanol molecules. They're not broken up into carbon, hydrogens, and water molecules. There might be some water molecules that are in there, but for the most part, the molecules that are down in this clear part are ethanol molecules, and the ethanol interactions. So inside of this are interactions between ethanol, which I'll draw this the CH3, and it's a bent molecule. Maybe it looks like this, maybe something like that. There are different kinds of atomic and molecular interactions. Remember, this oxygen has lone pairs of electrons that are stuck to it over there, right? Okay. So what can happen in something like ethanol is that you can get very strong interatomic or intermolecular bonding. Let's say, for example, I have another ethanol over here. Let's draw a chain, maybe O. Here's my lone pairs, and I have another. Let's draw a dashed line. I'll tell you why I'm drawing a dashed line for this in a second. Here's an oxygen, CH2, CH3. So here's another ethanol. Yeah, I could draw a box around that and say there's one ethanol molecule, and over here is another ethanol molecule I just drew nearby. And there's a hydrogen bond. So this hydrogen is weakly. Remember, this hydrogen carries a small delta plus, and this lone pair carries a small delta minus, partial charge. So there's an attractive interaction between this hydrogen, which looks a lot like a proton, a bare positive charged proton, and these lone pairs that are around this oxygen. Now, and that's a stronger interaction than this hydrogen to these hydrogens out here, which are partially positive. Remember, these have positive, or more positive than that negative oxygen. And you could go back through and calculate the formal charge of this oxygen and the formal charge of that hydrogen, and you get a very weak interaction between this hydrogen and that oxygen, and it leads to what is called a hydrogen bonding network. It's not as strong as a chemical bond, but it's fairly strong. The hydrogen bonding network is responsible for the fact that ethanol has a fairly low boiling point, or vapor pressure, compared to water. Water is a much lower vapor pressure, higher boiling point, and so ethanol will boil before water, because water would have two of these hydrogen bonds with it. But the hydrogen bonding network in ethanol is broken up a little bit, because you've got this alkane chain out here and hydrogen bonding going on in this part of the molecule. Okay, so the key is that in the condensed phase, this is the condensed phase, in the condensed phase, it's the intermolecular forces that dominate and determine the properties of the condensed phase. And so consequently, this is a very important area of study for multiple areas of chemistry and determine all sorts of things. Okay, so there are really three formal states of matter that are easy to understand. First of all, liquids are solid, liquid, and gas. So a gas is very low density, high kinetic energy, higher temperature, no structure, no local structure to the gas. A liquid is much more condensed, higher density, local structure, in the sense that if I, for example, I drew here, there's some local structure in this water. Even though this molecule can move around, it's breaking and forming these hydrogen bonds all the time. And so there's some local structure in a liquid, but as I move farther and farther away from one atom site to the next and to the next and to the next, I lose that local structure. So I could say that a liquid has short range local structure and no long range structure. A solid has perfect structure all the way through. If I look at a solid, it looks like a grid. If I look at the atomic ordering of a solid, in fact, here's a little cluster that I printed out. This was from a calculation that we did a long time ago, and you can see the packing of individual atoms in this particular cluster. This is, I think, a neon cluster that we studied quantum mechanically, and you can see this hexagonal packing around different faces of this crystal. So, for example, here, it doesn't focus so well. Maybe let's let it come into focus, and I'll use my pen. You have evidence of local structure. We have different facets of this thing, and so on and so forth. But there's local packing structure in a solid. This particular cluster was a small size cluster, and so there's different facets that emerge. So you can see, maybe you can see like there's a plane symmetry between these two, this half and that half, and so on and so forth. This was the part of a PhD thesis of one of my students, Sean Derrickson, about 10 years ago, looking at the packing structure of neon and light atoms using a fully quantum mechanical method that we had developed. And there's some asymmetries that you can see, like a five-fold symmetry around this axis. Let's see, can you see that right there? There's like this five-fold symmetry right here, right here. 1, 2, 3, 4, 5. And so, and then they have these hexagonal symmetries here. So a solid has all sorts of high symmetry characteristics, and very ordered and very basically ordered all the way out to infinity. If I were to take a cluster or take a solid and extend it all the way out to infinity, the location of every atom in that solid could be understood by simply looking at the location of the atoms in one repeating unit. Every repeating unit is carried on. So, and then a phase change is where you go from, so first of all, you can see a phase boundary between here and here. A phase change is where you go from one phase to the other, a liquid to a solid, or liquid to a gas rather. That would be the boiling. And you don't change the chemical nature. Ethanol in the gas phase is still an ethanol molecule. But you don't change the chemical structure. You simply you break these intermolecular bonds. And we can represent that on what's called a phase diagram. And a common phase diagram phase diagram. Phase diagram. We generally will plot things, for example, versus say pressure versus temperature. And so generally, as we increase the temperature, we might have a boundary between a solid and so high pressure, low temperature. You would expect something to be a solid. The solid can melt to form a liquid, or can form, as I have low pressure and higher temperature, I'm going to have a gas. And I might even have a boundary between the gas and the liquid. And I might have a boundary between a solid and a liquid. So this is a generic phase diagram for any single component material. The slopes and positions of these lines are important, and one can get from thermodynamics, but this is the general trend. So at high pressure, at high temperature, things form gases. As I decrease the temperature, keeping the pressure constant, so this would be at constant pressure here, I could go from, take a gas and condense it down to a solid. As I increase that, I might even have three components. I might have something that would go, maybe this is the atmospheric pressure is here, maybe this is 1 atmosphere. Okay, I'm just simply sketching something out. Okay, if this was our material at 1 atmosphere of pressure, okay, at this temperature would be the boiling point. At this temperature, drop that down right there, that would be the freezing point. Okay, that's the freezing point right there, and that's the boiling point. It's where at 1 atmosphere of pressure, I go from gas, which is on this side of the line, this is gas over here, to liquid. And as I continue to cool, this is the temperature, as I continue to cool, I go from liquid to solid. Now there's all sorts of different there's lots of information on this phase diagram that are important to point out. This point here is what's called the triple point. At that particular pressure and temperature, we can have a critical pressure and a critical temperature at PC and TC. So some critical temperature and some critical pressure. All three phases I can't write today. Coexist. Okay, at that particular point, all the three phases will exist, and it's difficult to get to that particular point because it's a very unstable. Any change or fluctuation in pressure or temperature pushes you away from that point. So it's a very unique temperature pressure point for a single component material, single component. For a single component material. Now if I added alcohol, or if I added oil or something to this, I would have a much more complicated phase diagram. And like I said before, the positions and everything of these lines and slopes of these lines are determined by the properties of the material. This point here, incidentally, is called the critical point. Okay, and that is called the critical point because if I'm at a high enough temperature, I cannot have a liquid. So if I'm at this particular high pressure and higher temperature up here, and I get past the critical point, the critical temperature, I cannot form a liquid. And so I can actually go from a gas to a liquid by going around the critical point and never undergoing a phase coexistence or phase transition. And that's an interesting phenomena. There's some really interesting work that's done examining the properties of what are called supercritical liquids in this region around the critical point. And there's some really fascinating statistical mechanics and material properties that exist moving through this particular region. And going from one region to another, for example, if I increase or decrease the temperature at 1 atmosphere, for example, going from liquid to gas, I see an abrupt phase transition between these two phases. I go from a liquid phase to a gas phase, a liquid phase to a solid phase, at an abrupt and definable temperature. I don't see that in this regime. The other thing which is important to point out from these phase diagrams is what's called the Gibbs phase rule. And the Gibbs phase rule, again, it follows directly from the laws of thermodynamics. And the Gibbs phase rule says that a single component system can have at most a triple point. I cannot have 4 phases simultaneously in the system. What would be 4 phases? Like, for example, in ice and other materials, you might have different solid phases. I might have a solid phase boundary someplace in here where I have like a solid 1 and a solid 2, corresponding to different packings of the crystal arrangement in a material, but I can never have more than 3 phases in coexistence for a single component system. And again, when you take physical chemistry or a more advanced course in thermodynamics, well, you can understand why that comes about. It has to do with the numbers of degrees of freedom that I have to specify the system. If I'm over here, yeah, I have the state of the system, it's gas, and I have temperature and pressure. And if I'm over here, I have a coexistence between pressure and temperature, and one of those has to be defined because I have solid and gas in equilibrium, 2 phases of the system. I have 1 degree of freedom, pressure or temperature, that I can vary along that line. So in other words, as I vary temperature, keeping phase coexistence, I have to also change the temperature or change the pressure to maintain that phase coexistence. When I get to this critical point, I don't have that freedom anymore. I have pressure and temperature both defined because I have 3 phases in coexistence. And likewise along here, I have pressure and temperature constrained to follow that curve because I have 2 components that are in equilibrium. And likewise along the solidus line, I have 2 phases in equilibrium, solid and liquid, and consequently pressure and temperature are not, I can't freely vary temperature and pressure. So in other words, I can't change the temperature without changing the pressure and maintaining the coexistence between these 2 phases, which is what I mean by this. I can't have more than 3 phases in contact and coexistence with each other in a single component system. Okay, so in water, let me roughly draw the phase diagram of water. It looks a lot like what I had up here. Temperature and pressure for water. Water is sort of a funny phase diagram. It looks a lot like what I just drew there. It has 3 phases. It has a solid phase, it has a gas phase, and a liquid phase. High density, lower density, and much lower density. And again, one could define the atmospheric pressure. Maybe we define 1 atmosphere here, and I could undergo along this line here. This point would be about the freezing point would be 0 degrees Celsius. This is 100 degrees Celsius are the normal freezing point and normal boiling points of water. Okay. Remember, this is at 1 atmosphere. 1 atmosphere of pressure. Normal freezing point, normal boiling point. There's a critical point that's up here, and a freezing point, or in a triple point, which I believe is 4 degrees Kelvin, or 4 degrees Celsius, and or 0.4 degrees Celsius roughly. It's a little bit above that, and I forget what the pressure that's necessary to do that. One could look that up if you wish. But this is much low density. Basically 1 gram per cubic centimeter, and pressure in atmosphere. Okay, and a little bit less. In fact, water has sort of an interesting property. If you look at the density of the liquid water versus the solid water, you might notice something sort of odd looking at the table that I have over to the left here. That the density of solid water is less than the density of liquid water, and that's unusual for most materials. And for most materials, it's the other way around. And in fact, the slope of this curve here is a little bit on the negative side, reflecting this fact that the solid has a lower density than the liquid. And so as a result, solid water, ice, floats on top of liquid water. For normal material, typical materials, this curve, the solid liquid phase boundary sort of has a slope like this. Water has a slope pointed this way, and it's a strange property of water, and it ultimately is tied back to this hydrogen bonding network that is present in water. So let's talk about hydrogen bonding network. So hydrogen bonding, there's 2 types of interactions that dominate the bonding or the structure of a liquid. First of all, hydrogen bonding, which I've alluded to here in talking about the ethanol interactions, and there's also what are called London dispersion forces. So London dispersion forces are basically the forces between everything else. It's not electrostatic. It's a higher order force, but it's important to understand. So let's first of all look at the kinds of forces that we can have in between atoms and between molecules. So the first thing are called dipole forces. So dipole force is basically, I have a charge distribution, delta plus, delta minus, and a delta plus. Let's just put a delta plus, delta minus, due to the fact that irrespective of the shape of this molecule, maybe it's got some sort of crazy shape to it. Maybe this molecule has a crazy shape to it. I have a center of charge, and I have a center of a positive charge and a center of negative charge, and I can calculate a net dipole moment of this molecule. And there's Coulomb interactions between those 2 parts are going to repel each other. Those 2 parts are going to repel each other, and these 2 parts are going to attract each other, and those 2 parts are going to attract each other. And so consequently, you tend to get an alignment of like, head to tail type alignments of these molecules, in a liquid. And this is just simply drawing something out randomly. It's of course, these things exist in 3 dimensions, but you get this sort of minimization of the electrostatic energy. But of course, these things are also moving around and wiggling and jiggling at kT at some thermal energy, and so you're constantly breaking and reforming these dipole interactions between one molecule and the other molecule, leading to the sort of fluid behavior of the molecule. And like it says over on the PowerPoint, they're about 100 times weaker than a chemical bond. Okay, about 100 times weaker, and the force decreases with the distance, and specifically the force decreases. So the force, or the interaction energy, let's say the V dipole of R goes something like 1 over R cubed. So it decreases as R cubed. So it's a little faster of a fall off than the Coulomb. Remember, V Coulomb goes as 1 over R. So this is a much shorter range interaction than the 1 over R interaction for Coulomb. But it's not as weak as London dispersion forces, which I'll describe next. So again, here's over at the left here. It shows a dipole-dipole network, and it's the net interaction of all these positive attractions and repulsions that lead to the properties of a dipole-dominated material, such as like ethanol, is dominated much by dipole-dipole interactions. Hydrogen bonding is one of the more interesting bondings in the sense that it's dipole-dipole in the sense that you have a hydrogen. For example, if I have an OH bond, and this is the rest of the molecule. Okay, it's got some blob up there, and I have another oxygen. Maybe over here, here's this hydrogen. Over here's the rest of the molecule sort of dangling off to the side here. I have these lone pairs that are on this this thing. So this hydrogen is attracted to that lone pair. Maybe if I can draw these out like this, little Mickey Mouse ears on my oxygen. This hydrogen is attracted weakly to that, and maybe over here's my other lone pairs. There's my 2 lone pairs of these 2 guys. Looks like little Mickey Mouse ears, I realize. Okay, but this hydrogen, which has a dipole, sees another dipole here. So here's a dipole for this thing, and maybe oriented positive to negative. Here's another positive to negative oriented along here. But this hydrogen can be fairly strongly attracted to this lone pair that's on this oxygen here. And in fact, one of the things that makes water is that it has two opportunities for hydrogen bonding, because in water I can also have this, draw the same scenario over here. Here's another. Maybe here's another hydrogen. These things are oriented in all sorts of different kinds of ways. And this hydrogen is attracted toward this guy. This guy's attracted over here. And in fact, it's not that hard to exchange a hydrogen between oxygens. And so maybe I could draw this out a little way. Maybe to look something like this: oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen. Let's say those 2 guys are bound to each other. Oops, that guy's already up. Here we go. And maybe this one's bound over here. Here's another hydrogen. Okay, so this isn't a bond. This is just a hydrogen bonds are the dots, and you see I've got this nice structure of Here's a water molecule. Right there, it's a definable water molecule. Here's a definable water molecule. This is a definable water molecule. But you see, this hydrogen can easily switch its allegiance, if you wish. I can easily swap out where these hydrogens are defined. Here I have a whole water molecule that's participating in this. Well, maybe I can draw the same structure. Let's see if I draw this. H, H, O, H, O. Maybe I can do something a little bit different. Well, maybe I can draw this guy here, and that one, right? And I give up that hydrogen, so maybe I can go from that to that, and I have he's now transferred over here, and has his own hydrogen still. And it's, so I didn't move any hydrogens around in doing that. I just reassigned who was hydrogen bonded to what, and rearranged some of the bonding. And there's not a lot of energy difference between this configuration of water and this configuration of water. And so consequently, these hydrogens that are in a hydrogen bonding network tend to move around very easily, even though it doesn't look like I've changed anything. I've just made this bond a little bit longer, and maybe this one a little bit longer, and this one a little bit shorter, and now I have, this is now my molecular unit. This is a new molecular unit, and here's a new molecular unit. Whereas down here I had, here I had a molecular unit this way. And here I had a different molecular unit. Okay? So it's very easy in a hydrogen bonding network to move the hydrogens around without really doing much. And this is extremely important process in water and in biological waters, especially because you see what I've done is I can introduce an extra proton into the hydrogen bonding network, and that extra proton can move through the system. Even though the physical proton hasn't moved, the charge can move very easily through the hydrogen bonding network. So proton and charge mobility in water is entirely dominated by this reshuffling of the hydrogen bonding network in a hydrogen bonded system. So probably one of the most important processes that go on in a biological system is motion of charges through membranes and motion of charges through a biological system, and it occurs via shifts in the hydrogen bonding network. So here I have over on the left is a little bit derived from the book of this idea of hydrogen bonding one's water molecules, and again showing that each water molecule has each oxygen has two hydrogens, and it's also hydrogen bonded to two other hydrogens nearby. And the definition, or how those hydrogens are defined, is really a function of the distance between the oxygen and hydrogen, and I can move around very easily between one hydrogen bonding network and another hydrogen bonding network by simply taking the diagram that's off to the left there and simply reorganizing the solid and dashed lines. And there's not a lot of energy that's required to do that. And in fact, it's less energy than the thermal energy of the system. And so I can easily move from one hydrogen bonding network to another hydrogen bonding network very rapidly and without a lot of effort, and consequently that gives rise to a lot of stability of something like water. The diagram that I have next to that shows roughly the distances between oxygens, which is about 28 angstroms, or 0.28 nanometers. And again, the hydrogen bonding angle is very, very similar to the internal bonding angle of the water molecule, 109.47 degrees. This is again is just simply a sketch of what I was showing before, that I can reassign the covalent and hydrogen bonds with a cost of very little energy. And this contributes dramatically to the motion and mobility of charges and protons in a hydrogen bonded network, especially a hydrogen bonded system such as water. And of course, anything that involves hydrogens typically will have hydrogen bonding, except for things that are like alkane systems and so on. So if I go back to my sketch of ethanol, hydrogen bonding typically does not occur between these alkane groups, these CH3 and CH. This CH3 and CH3 do not form hydrogen bonds, and methane does not form a hydrogen bonding a system. In fact, what I can show, and what was shown off to the left here, is how boiling point, the normal boiling point, varies as you increase different kinds of interactions. So almost no hydrogen bonding interactions whatsoever. Very weak forces between methanes. You wonder how does any methane interact with each other? We'll discuss that in a moment. Ammonia has strong dipole interactions. Remember, the structure of ammonia is as follows. The structure of ammonia is has a nitrogen, this sort of three-dimensional with a lone pair of electrons up here, right? And so you have a very strong positive, negative dipole interaction, but on methane, on ammonia rather, and methane. If you want to try to assign bond dipoles, you can understand why I have almost no dipole interactions whatsoever. So remember, this is a tetrahedral shaped molecule. So all of my bond dipoles, let's draw that in little positives and negatives, positive to negative, positive to negative, positive to negative, are pointed inward. So I have cancellation of dipoles. The net sum of that dipole is 0. Positive, negative, negative, positive. So that all of these, the net vector addition of these vectors is equal to 0. It's like I have two forces, one pulling that way, one pulling that way, and the net force on this point is equal to 0. So there's the net dipole of this molecule is equal to 0. So consequently, it has very, very low normal boiling point. So as you move across the periodic table, what you notice is the following: is that tetrahedral molecules have very, very low boiling points. It increases with the mass. It takes more kinetic energy to kick something into the gas phase. But you see very strong dipole interaction. So water again has this sort of weird behavior. Periodic trend would suggest that it would follow. Well, here's hydrogen telluride, hydrogen selenide, hydrogen sulfide. Well, maybe water looks a lot like hydrogen sulfide, but maybe I should predict its boiling point down here. But no, it's way, way up here, and there's a reason it has such a high boiling point compared to. Again, this is fluoric acid. Very, very, very dangerous stuff. And ammonia, very high boiling point because of the addition of this hydrogen bonding network. These are dipole interactions between here and here, and this is, again, this hydrogen bonding network kicking in. London dispersion forces are defined. They're not named after the city of London. It isn't something that happens that causes the where the police show up and break up riots. It's the London Dispersion Forces is named after London, the person London, and it is an interesting phenomena. It's a polarization phenomena. So the way you can imagine the electrons in a system are not static. Remember that in an electronic system we have a nucleus here with plus Z, and I have a cloud of electrons of minus Z charges that are around it, right? So I have this very localized nuclear core and a cloud of density, of electron density around it. And what can happen is if I have a small fluctuation, or just a little jiggle of the electronic force, of the electronic degree of freedom, or the electronic density around this nucleus, around this atom, well, another atom over here is going to respond, and so I'll have a fluctuation that leads to a polarization of this thing, and then comes back and interacts back here. So I get an instantaneous dipole, and maybe pointed that direction, but maybe pointed, and it induces a dipole around this thing, and because this is a 1 over R3 interaction, this is a 1 over R3 interaction, I get a 1 over R to the 6 attractive interaction. This is attractive interaction between dipoles, attractive interaction between dipoles. So I have a dipole-induced dipole type interaction in this system. So I get a 1 over R6 type interaction. This is the London dispersion forces. Okay, very, very weak. So the more polarizability, so the polarizability of something is how easily the electrons in that system can respond to a change in the electric field that it sees. So if you have many electrons, you have very high degrees of polarizability. So you have very stronger dispersion forces. Even atoms such as helium have dispersion forces. And so helium, which has, you would think, well, helium is a very nonpolar atom. I mean, it's a neutral atom. How can you get helium to condense and have helium-helium interactions? Well, those are the dispersion forces. You have these instantaneous fluctuations in the electronic cloud around the nucleus, gives rise to instantaneous plus minus, and that plus minus leads to an interaction, and that interaction leads to a 1 over R6 type attraction between atom A and atom B. So here's two neutral atom A's and B's. There's a little bit of a fluctuation. You can see this little pink cloud moves over and around atom B. Doesn't see it yet. It induces a dipole shift. So it sort of pulls a little bit of electron density. So atom B now sees, hey, look over here, I've got a positive charge. I'm going to move some of my electrons over here, but my nuclei aren't going to move. And so I see a little bit of plus minus, but of course it's a fluctuation, so it pops back into where it should be, and on average it looks like nothing happened, but it's the fluctuations around the equilibrium position that lead to this effect. It's like a dynamical type of a electronic interaction. Okay, so intermolecular bonds, very strong. Intramolecular bonds, very weak, very strong. Intramolecular bonds, very strong because you have covalent shared electrons between the different atoms. Intermolecular bonds are very weak, 100 times weaker at least, because I don't have shared electrons, but I have these other kinds of forces. London dispersion forces being the weakest, dipole-dipole interactions, and maybe I have Coulomb forces, but I also have hydrogen bonding forces that can go in. to the mix. And all of those contribute to the net intermolecular interaction in a condensed system. Okay, so a little quick check. Which of these are going to form stronger intermolecular forces? So nitrogen versus water. Let's say we have nitrogen at 1 atmosphere pressure and 300 degrees Kelvin, and water at 1 atmosphere and 300 degrees Kelvin. Clearly, if you want to do this experiment, this right here, volume, is about 70% nitrogen at 300 degrees Kelvin and 1 atmosphere pressure, and that is mostly water with some coffee at a little more than 300 degrees Kelvin and 1 atmosphere pressure. And water is in the condensed phase. It's a liquid. Nitrogen is a gas. So clearly, nitrogen forms much, much, much weaker intermolecular forces than water. Okay, here we have ethanol and dimethyl ether. Okay, the boiling points of the two. Which one is going to have a higher boiling point? Based upon what we know. So we can think about this and look at ethanol. We've discussed ethanol. Here's ethanol right there. Okay, it can form hydrogen bonds. This hydrogen can form a hydrogen bond with another ethanol molecule, and seeing the lone pairs of this. These hydrogens aren't so happy about these lone pairs. It might form weak hydrogen bonds, but this hydrogen is a much more polar hydrogen than these hydrogens. So what you would suspect is that even though the mass of ethanol and dimethyl ether are the same, this has a much, much lower boiling point, much higher vapor pressure than ethanol. In fact, this is a very volatile organic substance. Okay, and likely, which gas would be more ideally at the same pressure and temperature? Remember, ideal gases, no interactions, weak at best interactions. So what you would guess then, based upon the fact that carbon monoxide over here, dipole interactions are going to be much stronger than in nitrogen. So consequently, one would expect that carbon monoxide behave less ideally at the same temperature and pressure than nitrogen. So nitrogen is a pretty ideal gas, and carbon monoxide is certainly probably not a very ideal gas. Okay, so characteristics of liquids. There's a liquid, right? Low compressibility, not very rigid, high density. Now, there's a tension called surface tension between the gas phase and the liquid phase. The other thing which you might be able to see, I don't know if you can see the capillary action between this or not. Let's see, can I see that? I'll point this up a little bit. So you see a little tube that's inside of that, right? Okay, so you notice that, so the tube is mostly made out of plastic, and you might notice there's a little bit of a creep of the water or of the ethanol up the side of that tube, right? Okay, there's a couple things you might notice on this. First of all, let's see if we can see that right. Can't see it so clearly. Move the light a little bit right there, maybe. Hard to see it. But if you look, yeah, you can. Okay, you see a little bit of a creep up the side of the tube of the ethanol going up, and that's capillary action. If you also look very closely, you'll notice that it's slightly cupped. It's slightly cupped. If I look at the side of this tube, you'll notice that it's slightly cupped like that. That's called a meniscus. That's called the meniscus, and this meniscus is it's due to a competition between the adhesive and cohesive forces. So there's an adhesive force or cohesive force that causes the ethanols to attract each other. So the ethanol or the liquid that's inside of this is very attracted to each other and wets the side of the tube. You can also have a negative meniscus. You can have something like mercury, for example, which would form a negative meniscus like this. And so in which case I get very, very, this is the capillary tube, very weak interactions between the mercury and this is water. So the mercury liquid forces are very, very weak and very and form a negative meniscus, whereas the water and ethanol and other things that have very strong hydrogen bonding tend to form meniscuses that look like this. Okay, and so again, this is sort of a convex meniscus. Let's spell that word: meniscus. Meniscus is what that's spelled. That meniscus. Okay. SC meniscus. Let me write that again. Well, you can see it in there we go, meniscus. There you can spell it correctly. Okay, so here you have mostly, well, this is some sort of hydrocarbon or maybe glass or plastic or something, and you will form, and it's a network of positive and negatives, and you get a network that sort of creeps up the side due to interactive forces between the water and the glass or plastic that's on the meniscus. And in mercury, it's very, very weak interaction. It's this convex meniscus. So concave, like this, convex means that. Okay. Viscosity is simply a measure of resistance to flow. So something that's highly viscous, like syrup, for example, it resists flow. Things that tend to have high degree of hydrogen bonding tend to be very viscous. Water has a higher viscosity than ethanol. Glycerol has a higher viscosity than water, all due to the fact that it has more opportunities for hydrogen bonding. And then lastly, we can study the properties of liquids spectroscopically in various ways to do this. Without going into a lot of the detail of how we study to study these. For example, we can do neutron scattering. We can do scattering experiments to probe the instantaneous structure, or the average structure rather, of water. We can do pulsed X-ray, very fast X-ray scattering now, to look at instantaneous structures of water. And you can also do experiments where you have a molecule in a water cavity, and you excite that molecule with a pulse of radiation, pulse of light, change the electronic state of that molecule, and look at how that state relaxes as a function of time, and from that pull out ideas of what's going on in the water itself. This is the kind of research that people in physical chemistry would do, studying the interaction between molecules and their environment. So I'm going to end today on that, and we'll continue the discussion. The study of structures, study of liquids and solids is the topic for the rest of the term, and for the next couple of weeks, that's what we'll be talking about. Stay safe, maintain your social distancing. This is the cheapest form of hand sanitizer you're going to get. This is just simply 100% ethanol and a little pump bottle. Cost me, I don't know, a dime. And use it, spray it on your hands, wash your hands, use soap, and stay safe. And I'll hopefully see you all in person at some point in the future once we get back to campus. That's all for today.